So today we're going to talk about elastic collisions. We talked before about how in both elastic and inelastic collisions, momentum is conserved. However, it's only in the elastic collisions that the kinetic energy is also conserved. So what we're going to focus on today is we're just going to worry about the conservation of momentum to solve these problems. Now, I know that before I was talking like we're not going to mess around with elastic collisions and the math that relates to it, and that was going to be true. However, with the extra time that we're going to have, we're not going to have state testing, we don't have to worry about NWA as far as I know. I figured, why not? I'm not going to put this information on the test because I don't think it would be fair. However, we're going to do some practice problems and I teach you about one-dimensional elastic collisions. Now later on this week, Miss Jacobson is going to give you a take-home activity that's going to cover both elastic and inelastic collisions. So I think that maybe learning about some of the elastic collisions and we're looking at the conservation of momentum is going to help you to understand when you do this activity better how elastic collisions work. So I've set up two problems here. Remember, in an elastic collision, the two objects bounce off of each other, or maybe one object bounces off of the other, depending on how the collision goes. In inelastic collisions, the objects stay together. So since these are elastic collisions, we've got a scenario, we've got one ball that's going to strike another ball, and the second ball here is motionless, while this ball is moving to the right at 4 meters per second. After the collision, in this scenario, all of this object's momentum is going to be transferred to the stationary object. So what's going to happen is this object on the left here, the one that's originally moving, is going to become stationary, while the object on the right will continue, or not continue, but begin to travel to the right in the direction that this object was traveling in. So if you think about a pool shot, generally when you hit the cue ball straight on at another ball, after the collision that cue ball stays stationary and the ball that was struck begins to move. And so all of the momentum from the cue ball, which would be this ball in that scenario, would be transferred to the ball that was struck. So this is the exact sort of scenario we're looking at. It's a one-dimensional elastic collision. And so since we know all of the collision from this ball is transferred into this ball, we know that this ball will become stationary and this ball will start to move. And so what we're going to look at is we're going to calculate the total momentum in the system. So if you remember, we did m1v1 plus m2v2 before in the inelastic collision. In this scenario, we don't need to do m1v1 plus m2v2 to find the total momentum, because the only object that has momentum in this problem is the moving object, or the object that's on the right. So the total momentum starting out in this system is just in this ball that is on the left here. And so to calculate this momentum, we're going to take basically mass times velocity. So our mass is 3. So mass times velocity equals momentum. So our mass is 3 and our velocity is 4. So our momentum is 12 kilograms times meters divided by seconds. So we were talking before how all of this momentum from the ball on the left was going to be transferred to the ball on the right. And so this ball would become stationary and this ball is going to be moving to the right. So the question here that we want to figure out is, how fast is this 4 kilogram ball that was stationary going to be traveling? What will its velocity be after the collision occurs? And so to do that, we're going to take the total momentum of the system, which is 12 kilograms times meters divided by seconds. And because the momentum is conserved in this scenario, we can take this equation, P equals mv, and now we're looking at the second object. We know that our P is 12, because it's always going to be 12 in this system because of conservation of momentum. We know the mass of the ball isn't going to change. It's still going to be 4 kilograms after the collision, equals 4. And what we're looking for is V. What does V equal? And so this is a pretty straightforward problem, right? Because momentum is 12, our mass is 4, we don't know the V, but 3 times 4 equals 12. So our velocity must be 3 meters per second. So in these one-dimensional problems where there is a collision between a moving object and a stationary object, an elastic collision, what we're going to see is that the momentum is always transferred to that stationary object completely. And so that's a head-on, one-dimensional collision, just like you would see in some pool shots. So this is how we're going to calculate it. We're going to calculate the momentum from the system, which is all inside this one moving object. And then we're going to say that that momentum is transferred completely to the stationary object. And once we do that, then we can calculate the velocity or the resultant velocity of that object after the collision. So now we know that this 4 kilogram object after the collision will be moving 3 meters per second to the right. So this is a one-dimensional elastic collision with one moving object and one stationary object. So that's pretty straightforward. It's really, really simple, this type of collision is. But a more complex type of collision is shown below. In this scenario, we have two objects that are traveling towards each other. All right. One is a mass of 2 kilograms and a velocity of 3 meters per second. The other has a mass of 5 kilograms and a velocity of 2 meters per second. But you gotta understand these velocities are in opposing directions to one another. And since velocity is a vector, this needs to be viewed as negative 2 meters per second. So after the collision, obviously the mass is going to stay the same. The object on the left is still going to have 2 kilograms of mass, and the object on the right is going to have 5 kilograms of mass. But the question mark is, the object on the left, we don't know its resultant velocity. However, we're given the resultant velocity of the object that's on the right. So we're going to work above here, and we're going to use the exact same equation we looked at before. M1v1 plus M2v2 equals MF_VF. So mass final times velocity final. However, because we have two masses in the resultant, we're going to do M1v1 plus M2v2 equals M1v1 plus M2v2. So we're looking at the mass final and the velocity final of the first object, but we're also looking at the mass final and the velocity final of the second object. They're separate still. So check this out. We'll write this out. M1v1 plus M2v2 equals M1v1 plus M2v2. So now we've got two objects and two objects, and we're going to keep them consistent. So the mass of the first object is 2. The velocity of the first object to start is 3 plus. The mass of the second object is 5. And since this object is traveling to the left or in a negative direction, its velocity is -2 equals M1v1 plus M2v2. Mass of this first object is still 2. We don't know its velocity, so we're just going to put V in for its velocity. Mass of the second object is 5. And its velocity is 1.5 meters per second. Now, in this problem, you have to be given one of the resultant velocities after the collision, otherwise you'd never be able to solve for the velocity of the other object. So it's important in these sorts of problems, you're going to be given one of the object's velocity after the collision, otherwise it's unsolvable. But regardless, pretty straightforward. Momentum of the first object plus momentum of the second object equals momentum of the first object plus momentum of the second object, and we just plug in our numbers from the objects before and after the collision, and then we solve for the one variable that we don't know. And it's always going to be a velocity because the mass of those objects in a perfectly elastic collision, they're not going to change. They can't change, otherwise we have too many objects to worry about. So this is still a one-dimensional collision, two objects, and it's elastic collision. So we're going to go ahead and solve this. 2 times 3 is 6, and then 5 times -2 is -10. 6 minus 10 is going to be -4. So our momentum before the collision is -4 because this object has more momentum with that larger mass, even though it's got a smaller velocity than the object over here on the left. And then after the collision, we have 2v plus 5 times 1.5. So plug in the calculator really quick. Should be 7.5, but I'll just double check. So it is 7.5. And now we need to solve for the v here. And so this is a pretty straightforward multi-step algebra problem. So we're going to subtract both sides by 7.5, or from both sides 7.5, and we'll get a -11.5 over here equals 2v. And then we're going to solve for v, and that's just going to involve dividing both sides by 2. And -11.5 divided by 2 is going to be -5.75 meters per second. Now, this answer that we're given is going to be the velocity right here. -5.75 meters per second. So that means that our object, that 2 kilogram object that was traveling to the right in the beginning, is now going to be exiting this collision to the left, and it's going to be given a higher velocity than either of the two objects had to begin with. Maybe you remember back when we were messing with the air track on that Thursday before we got let out of school for the extended spring break, that the more massive object, those two carts that were traveling slowly together, when they struck that one cart that was also traveling pretty slowly, that one cart would leave with a faster velocity out of the collision than either of the two objects had going into the collision. And that's because in order for momentum to be conserved after the collision, if a less massive object is struck by a more massive object, it has to have a higher velocity in order for the momentum to be conserved. So it seems a little counterintuitive that either of these two objects could have a larger velocity after the collision than they had before, but that's what has to happen when you have a less massive object struck by a more massive object in order for momentum to be conserved. And so it's really straightforward. We're just going to take momentum of the first object, momentum of the second object, add them together. That's our total momentum. And then we're going to take the momentum of this first object after the collision and add it to the momentum of the second object after the collision in order to solve for whatever variable we're looking for, which is always going to be one of the velocities. Now, this could get really fancy, and you know, you could even do this sort of problem and be like, okay, we know the velocity of the two objects after the collision, and we know their masses. How fast was one of the objects going into the collision before it occurred to get this result? And once again, as long as you know one of the velocities but not the other, you can still solve for it on this front end. You'd use this exact same equation, but instead you'd have all of these variables filled in over here and be solving for one variable over on the left side. So these problems are really straightforward. You always be solving for one variable. Obviously it involves a lot more numbers than the inelastic collision problems, but still at the end of the day, it's the same thing. It's the conservation of momentum, and the conservation of momentum is what allows us to solve for these velocities as long as we know all but one of the variables. So I'm going to go ahead and give you some elastic collision problems. You should see that assignment on Google Classroom listed for today. There's just a couple. I'll probably have you practice some more inelastic and elastic collision problems tomorrow, which is going to be on Wednesday, and you'll see that assignment as well. Basically, just to get your head wrapped around these sort of one-dimensional elastic and inelastic collisions.